Physics, at its heart, is our human attempt to write the rule book of the universe. And for the last century, we've had two astonishingly successful sets of rules. One is Albert Einstein's general theory of relativity. It's the law of the big. It describes gravity not as a force, but as the elegant bending of space-time by mass and energy. It governs the waltz of planets around stars, the spiraling dance of galaxies, and the gentle fall of an apple from a tree. It's a masterpiece of cosmic architecture, tested and proven to be incredibly accurate in the realm of the very large. It is our guide to the cosmos on the grandest of scales. Then we have the other set of rules. This is the law of the small, the strange, the utterly bizarre world of quantum mechanics. This theory describes the universe at the level of atoms and the particles within them. It's a world of probabilities, not certainties. A world where particles can be in many places at once, and where tiny packets of energy, or quanta, are the fundamental currency of reality. Quantum mechanics underpins so much of our modern world, from the silicon chips in your phone to the medical lasers in our hospitals. It is, without a doubt, the most successful scientific theory we have ever conceived. Here, though, is the great puzzle, the deepest mystery in all of modern science. These two pillars of understanding, general relativity and quantum mechanics, simply do not work together. They speak different languages. One describes a smooth, continuous, geometric universe. The other describes a jittery, pixelated, probabilistic one. When we try to use them in places where both should apply, like in the heart of a black hole or at the moment of the Big Bang, the mathematics breaks down. The equations scream at us with infinities, telling us that our rulebook is incomplete. So, what do? We have two perfect descriptions of the universe, one for the large and one for the small, but they contradict each other. It's as if we have a perfect map of the oceans and a perfect map of the continents, but they don't fit together to form a single, coherent map of the Earth. Finding that unified map, a single theory that can describe everything from a falling apple to a fleeting electron, is the grand quest of modern physics. We call this undiscovered theory quantum gravity, and finding it is the challenge of our time. Why is it so incredibly difficult to find this theory of quantum gravity? You might think we could just run some experiments to see how gravity behaves on a quantum scale, but here we run into a monumental obstacle. Gravity, you see, is astonishingly weak. Think about it. A simple little fridge magnet can defy the gravitational pull of the entire planet Earth to hold up a piece of paper. The force of gravity is trillions upon trillions of times weaker than the other forces of nature, like electromagnetism, that govern the quantum world. This weakness makes its quantum effects almost impossibly small. To see the quantum nature of gravity directly, we would need to probe nature with unimaginable energies. We would need to create conditions so extreme that they haven't existed since the first fleeting moments after the Big Bang. To do that, we would need a particle accelerator, a machine to smash particles together that is the size of our entire galaxy. That is, of course, far beyond anything we could ever hope to build. So for decades, the search for quantum gravity has been a theoretical one, a pursuit confined to blackboards, supercomputers, and the brilliant minds of theoretical physicists. This has left us in a difficult position. Without experiments, without data from the real world, our theories of quantum gravity are just beautiful mathematical ideas. We have things like string theory and loop quantum gravity, both of which are incredible intellectual achievements. They offer tantalizing pictures of what reality might be like at its most fundamental level, with vibrating strings or tiny loops of space-time. But they make very few predictions that we can actually go out and test in a laboratory. It's like being a detective with a list of suspects but no fingerprints, no DNA, no evidence to point the way. This is why physicists are always searching for clever, indirect ways to get a glimpse of the quantum nature of gravity. We can't build a galaxy-sized machine, so we have to be smarter. We look for tiny clues, subtle hints left behind in the cosmos. Perhaps in the faint afterglow of the Big Bang, or in the light from distant exploding stars. But even these are incredibly difficult to find and interpret. The dream has always been to bring the search for quantum gravity out of the realm of the cosmos and into the laboratory, where we can control the conditions and test our ideas directly. What if we've been looking at the problem in the wrong way? What if, instead of trying to create colossal energies, we could look for a very, very subtle effect right here on Earth? This is the beautiful idea behind a new generation of experiments. It's a shift in thinking. Instead of trying to shout at the universe with immense power, we are trying to listen very carefully for a faint whisper. And one of the most exciting of these new ideas involves something you see every day. Something that seems utterly simple, but holds profound secrets. A beam of light. The central idea is to use a rotating beam of light to try and tickle space-time, just a little bit, to see if it responds in a quantum way. The experiment is born from a fascinating theoretical prediction. Some theories of quantum gravity suggest that if you accelerate an object, it might experience a kind of friction as it moves through the vacuum of space-time itself. This isn't friction in the normal sense, like air resistance. It's a much deeper, more fundamental effect, arising from the quantum jitters of space-time at the tiniest possible scales. An object moving through this quantum foam might lose a tiny bit of energy. Now, accelerating something like a cannonball to see this effect is impractical. But we can accelerate something else. We can accelerate light. How do you accelerate light? Well, light travels at a constant speed, of course, but you can change its direction. Forcing a beam of light to travel in a circle is a form of acceleration. And we can do this very, very fast. By spinning a beam of light around at incredible speeds, we can create a highly accelerated system in a controlled laboratory setting. This gives us a tool, a new kind of probe, to search for these predicted quantum gravity effects. This approach is ingenious because it sidesteps the need for universe-breaking energies. It transforms the problem from one of brute force to one of extreme precision. Can we build an experiment sensitive enough to measure an almost infinitesimally small loss of energy from a spinning beam of light? If we can, we might just be able to see the first experimental evidence of a link between the world of gravity and the world of the quantum. It's a bold and brilliant attempt to open a new window onto the deepest laws of nature using tools we can build today. So, how do you actually build an experiment to do this? It sounds like something from science fiction, but the components are, in a way, quite familiar. The setup is elegant in its simplicity, though incredibly demanding in its execution. At its core, you need three main parts. First, you need a source of very pure, very stable light. This means a high-powered, single-color laser. The laser beam is our protagonist, the hero of the story that we are sending on a journey to probe the fabric of reality itself. Its stability is crucial. We need to know its energy with exquisite precision before we send it on its way. Next, you need to make the light spin. This is the job of the second key component, a rapidly rotating mirror or a similar optical device. Imagine a tiny mirror, polished to perfection, spinning on its axis billions of times per second. When the laser beam hits this spinning mirror, it's sent on a circular path. The light itself is now in a state of constant acceleration. The faster the mirror spins, the more extreme the acceleration and the greater the chance of seeing any potential quantum gravity effect. This spinning system is the heart of the experiment, the engine that powers our search. Finally, after the light has completed its spinning journey, you need to catch it and measure it. This is the role of the third part, an ultra-sensitive detector. This detector's job is to measure the energy of the light beam with incredible accuracy. It has to be sensitive enough to notice if even a single photon, a single particle of light, has a slightly different energy than it should. The whole experiment boils down to a simple comparison. Is the energy of the light beam, after it has been spun, exactly the same as the energy it had before? Putting this all together, you have a tabletop experiment searching for the secrets of the cosmos. A laser fires a beam of light. A spinning mirror sends that light on a dizzying, accelerated journey. A detector waits at the end to perform a meticulous health check, looking for any sign that the journey has tired the light out, that it has lost a tiny, almost imperceptible amount of energy. The beauty is in its directness. We are asking a simple question of nature and have built a machine capable of hearing the faintest possible answer. What exactly are the scientists looking for? Well, they are on the hunt for a discrepancy, a tiny anomaly that, honestly, just shouldn't be there according to our current classical understanding of physics. According to all the laws we know, a beam of light reflecting off a perfect mirror in a vacuum should not lose any energy. There's no air resistance, no friction in the conventional sense. The light going in should have exactly the same energy as the light coming out. Our standard rulebook is very clear on this point. Any deviation from this would be, to put it mildly, revolutionary. The hypothesis of the experiment, however, is that our standard rulebook is incomplete. The theories of quantum gravity suggest that the story is more subtle. As the light beam is whipped around in its circular path, it is interacting with the very fabric of space-time. If space-time has a quantum, grainy structure, then this interaction isn't perfectly smooth. It's more like a boat, moving through slightly choppy water than a skater on perfectly smooth ice. This space-time friction could cause the light to lose a minuscule amount of energy. It's this specific energy loss that the experiment is designed to detect. This predicted energy loss would be incredibly specific. It would depend on the speed of the rotation and the energy of the laser. This is important because it allows scientists to distinguish it from other, more mundane sources of error. For example, the mirror might not be perfect, or it might heat up slightly, which could also affect the light. But a genuine quantum gravity signal would have a unique signature. It would change in a predictable way as the experimenters change the spin speed of their mirror. This allows them to filter out the noise and be confident that what they're seeing, if they see it, is real. So, the scientific goal is to measure the energy of the light with enough precision to see if a tiny fraction of it has gone missing. It's not a dramatic explosion or a flash of new particles. It is the quiet absence of something that should be there. It's like, meticulously counting every grain of sand in a bucket before and after shaking it, just to see if a single grain has vanished into another dimension. The challenge is immense, but the clue they are looking for is clear. A tiny, rotation-dependent energy loss that classical physics simply cannot explain. To say that the expected effect is small is a cosmic understatement. It is almost incomprehensibly tiny. Let's try to get a sense of the scale we're talking about. Imagine you have a light bulb, a standard 100-watt light bulb. That bulb is pouring out a huge amount of energy every second in the form of photons, the particles of light. The energy loss that this rotating light beam experiment is looking for is about a billion times smaller than the energy output of that single light bulb. It is a whisper in a hurricane, a single drop of water in all the oceans of the world. This is why these experiments have been impossible until very recently. We simply didn't have the technology to measure things with this level of precision. It requires lasers that are incredibly stable, detectors that can essentially count single photons, and an ability to control vibrations and temperature to an almost perfect degree. Even the slightest tremor from a passing truck or a tiny change in the room's temperature could completely swamp the signal you're looking for. The experiment is as much a triumph of engineering as it is of theoretical physics. It pushes the boundaries of what is technologically possible. But here is why this tiny number is so profoundly important. In physics, it's often the small cracks that bring the whole building down. At the end of the 19th century, there were just a couple of small, niggling problems with classical physics. One was about the nature of light from hot objects, and the other was about the orbit of the planet Mercury. These seemingly minor issues led to the two great revolutions of the 20th century: quantum mechanics and general relativity. Small anomalies are where new physics hides. They are the clues that tell us our current understanding is not the final word. So, while the energy loss itself is minuscule, its implications are monumental. Finding it would be like discovering a fossil of a creature that shouldn't exist according to our current theory of evolution. It wouldn't just be a new piece of data. It would be a signpost pointing the way towards a completely new and deeper understanding of reality. It would tell us that our quest for a theory of quantum gravity is on the right track, and it would provide the first concrete, experimental piece of evidence to guide us on that journey. The size of the effect doesn't matter. Its existence is everything. If this experiment, or one like it, were to succeed and detect this predicted energy loss, the consequences would be profound. It would be the first ever experimental evidence for a phenomenon that lies beyond our two great theories of physics. For the first time, we would have a tangible, repeatable laboratory result that points directly to the unification of general relativity and quantum mechanics. It would be a moment in science on par with the discovery of the Higgs boson, or the first detection of gravitational waves. It would signal that the era of quantum gravity is no longer just a theoretical dream. Such a discovery would immediately provide crucial guidance for our theories. As we've seen, theorists have developed several different candidate theories for quantum gravity, like string theory and loop quantum gravity. These theories make different, subtle predictions about the nature of spacetime at the quantum level. A positive result in this experiment would help us distinguish between them. The exact amount of energy lost and how it changes with the rotation speed would act as a filter. It would allow us to rule out some theories and lend support to others. It would turn a purely mathematical debate into one grounded in experimental fact. Beyond just confirming a theory, a successful experiment could reveal entirely new properties of spacetime. Is spacetime fundamentally smooth, or is it grainy? Does it have a fizz or foam to it at the smallest scales? Does the vacuum of space itself have physical properties we've never been able to measure before? This experiment could begin to answer those questions. It could transform our view of empty space from a passive empty stage into an active, physical medium that can interact with the things that travel through it. This would be a radical shift in our conception of reality. Furthermore, a confirmed result would inspire a whole new field of experimental physics. Once you know that such a subtle effect is detectable, you can design more and more precise experiments to probe it further. You could try different types of particles, different configurations, and different levels of acceleration. It would open up a new frontier, a new way of exploring the universe, not by looking out into the cosmos with telescopes, but by looking down at the very fabric of reality on a laboratory bench. It would be the beginning of a new kind of exploration, every bit as exciting as the voyages of the great explorers. The true beauty of this experiment lies in its role as a potential bridge. It seeks to connect the two most disparate realms of our physical understanding, the macroscopic world of gravity, stars, and galaxies, and the microscopic world of particles, probabilities, and quanta. These two worlds have remained stubbornly separate in our theories for almost a century. This experiment offers a tangible way to build a bridge of data between them, allowing knowledge to finally flow from one to the other. It's an attempt to find a common language that both sides can speak. Think of it as a Rosetta Stone for physics. The original Rosetta Stone allowed us to understand ancient Egyptian hieroglyphs because it had the same text written in a language we already knew, Greek. In this experiment, the spinning beam of light is our text. We understand its properties perfectly through the language of classical physics and electromagnetism. If we see a deviation an energy loss. That is the text written in the unknown language of quantum gravity. By comparing the expected behavior with the observed behavior, we can begin to decipher the grammar of this new fundamental language of nature. This bridge would not just be for theorists. It would change the way we think about the universe at a fundamental level. Our current picture of reality is schizophrenic. We have to switch between the smooth, geometric world of Einstein and the jittery, probabilistic world of quantum mechanics depending on the problem we're looking at. Finding a connection, a link, would show us that underneath it all, there is a single, unified reality. It would reassure us that the universe is, at its deepest level, coherent and understandable. It's a search for the ultimate unity in nature. And this bridge could eventually lead to entirely new technologies. This is a long way off, of course. When electromagnetism was first being explored in the 19th century, no one could have predicted it would lead to the internet and global communications. When quantum mechanics was being developed, no one imagined it would lead to computers and MRI scanners. By gaining our first experimental handle on the quantum nature of spacetime, we may be laying the groundwork for technologies we can't even begin to imagine today. It is by exploring these fundamental frontiers that we plant the seeds for the revolutions of the future. So, where does this leave us? We stand at a thrilling moment in the history of science. For decades, the quest to unite gravity and the quantum world has been a journey through a dark, theoretical wilderness with no map. We've been guided only by mathematics and the principle of beauty. But now, with experiments like the rotating light beam, we are seeing the first glimmers of dawn. We are developing the tools to finally bring this search into the laboratory and ask direct questions of nature itself. This is a monumental shift. Whether this specific experiment finds the effect it's looking for or not, its importance is undeniable. It represents a new philosophy, a new way of tackling one of the greatest challenges in all of science. It is a testament to human ingenuity, the ability to reframe a seemingly impossible problem into one that can be solved with cleverness and precision rather than brute force. It is part of a wave of new, high-precision, tabletop experiments that are opening up a new front in our exploration of the universe. The era of armchair quantum gravity is ending, and the era of experimental quantum gravity is beginning. This is what makes being alive, right now, in this particular moment of cosmic history, so exciting. We might be the generation that sees the first crack in the wall separating our two greatest theories. We might be the ones who get the first glimpse of the unified theory that governs all of reality. This is not just about filling in the last few blanks in our textbooks. It's about deepening our relationship with the cosmos, about seeing the universe in a new light, and about understanding our place within it on the most fundamental level possible. The search for quantum gravity is a deeply human adventure. It's driven by that innate curiosity that makes us look up at the night sky and wonder. Experiments like the spinning light beam are the next step in that grand journey. They are our modern-day sailing ships, built not to cross oceans, but to navigate the strange and beautiful territory where space, time, and the quantum world meet. The journey is just beginning, and what we find there could change our picture of the universe forever.